All right, so we're going to talk about the extreme value theorem. So what it says is a continuous function on a closed interval obtains both its maximum and its minimum on that interval. And we'll see that this continuous part becomes real important along with this, with this closed interval. Those two work hand in hand. So we'll talk about a maximum and a minimum and what it looks like algebraically. So if I'm talking about a maximum value of the function y is equal to f of x at x equals c, what that means is that, the function is the biggest at that particular value. So for that to happen, it means if I evaluate f at c, it's going to be greater than or equal to all the other values that I evaluate. Now, if you want to say it's the only maximum, then we could, erase this. But it is possible you might have two maximums. So we could say it has a maximum at c, maybe even another like c2, for instance. So that's why I have less than or equal. Now, a minimum value would say that this function is, its smallest value at the c value. So that means, the evaluation of f at c is going to be less than or equal to the evaluation of f at any other x value. Now, to kind of show you this extreme value theorem, I'd like to just kind of show you some pictures of a function, a continuous function on a closed interval. We'll see why it always obtains its maximum and minimum. So if I have, a function, and what I want to do is just do a picture of a continuous function on a closed interval. So let's say from A to, B over here. So that means, it's defined here, so that's why it's going to be closed at that particular point. And then, this being continuous all the way to B, and, who knows the shape of it. I'm just trying to form some continuous function from A to B. Now, what we know is that this function will always obtain its absolute maximum or absolute minimum on this closed interval. What we can see is that in this particular picture, this happens to be its minimum value, which happens to be the endpoint A. So, f of A is less than or equal to all the other values. And we can see that there's some c value here, that value right there, which is going to be its absolute maximum, which means this function, this f function evaluated at c is going to be bigger than all the values as well. Now, it could have more than one of these. It doesn't always mean that this has to be the maximum or endpoints have to be the minimum. We'll see various pictures of different functions. But what I can guarantee you is as long as it's a continuous function on a closed interval, there will be an absolute max and there will be an absolute minimum. Now, if I look at, say, y is equal to, say, 1 over x, and we'll say, like, on the interval, I don't know, say from minus 1 to 1. It doesn't have to be a symmetric interval, but let's just say from minus 1 to 1. Why would this function not be considered for this extreme value theorem? Well, it doesn't only have to be, it has to be continuous and also has to be at a closed interval. So what I can see is that this is a closed interval, but this function is not continuous on this closed interval. So if you look at, our symmetric interval from -1 to 1, we'll do it in a different color. What I know is that 1 over x looks like this. Now I did say a closed interval, so let's pop it on these closed intervals here. So here, and then here. So a closed interval. Notice that this function on this closed interval doesn't have a maximum. It also doesn't have a minimum because there's no value for which I can say that all the other values are beneath. You might say, well, hey, that is going off into a maximum value, but, since this thing is asymptotic to 0, I can't really nail down an individual c value, because for every c value that I find, let's say 1/2, you can say, well, 1/2 is the maximum value. Well, that would be here, and I'd say, well, I can find another maximum value. I'll just go to like a quarter. And you're like, well, I can find another maximum value. I'll just go to 1/8. So if I, continually cut that in half, I can see that I can get, larger values. So there's no one point we can nail down. All I know is that as I get really, really close to 0, this thing gets really, really close to infinity. So that's why no absolute maximum, no absolute minimum in this case, because, it fails to be continuous. Let me pause it. I'm going to do the definition for critical values so we can kind of spot these things. So what I want to define for critical values are things that look like this. So I know that the absolute maximum minimum could happen at these endpoints, but also tends to happen at these values here, where this function changes from, increasing to decreasing. And we'll notice that the slope of the function right here happens to be 0. So we're going to use this kind of idea to find candidates for possible maxes and minimums. So let me put that definition up there. All right, so the first derivative test. So if f has a local extreme value, we're talking about a local maximum or a local minimum at x equals c, then f prime of c is equal to 0, or f prime of c is undefined. Now, most of your calc books will just simply state this, but this undefined I also like to consider in case we have something that is sharp. And I'll show you some pictures to kind of verify this part as well. Now, these c values, so these x equals c values, are going to be called critical points. Now, we have to be careful because this is like only an if-then statement. It says if it has a local extrema, so we're talking a max or minimum, then, its derivative is equal to 0 there. Or this. But then its derivative is equal to 0. But just because its derivative is equal to 0 does not guarantee that it has a local maximum or a local minimum there. So what we showed is, and what we mean about local is we're talking about around that particular point. So if I have a continuous function, let's just say something like this. Now, I'll put it on a closed interval, but it's not really necessary in this case. What we're really looking at is we're looking at these critical values. So these points right here happen to be the critical values of this function. And the reason why I know that is because the slope at all these points happen to be equal to 0. So, its derivative will be equal to 0 here, its derivative will be equal to 0 here, 0 here, 0 here. So, this might have a C1, a C2, a C3, and a C4. And notice that, these are local maximums. So if I'm only looking at this graph around that particular point, this point is larger than all the other points around it. In the neighborhood of this point, you can see that this one's a local minimum, this is a local maximum, and this is a local minimum. Now, I said to be careful. Just because the derivative is equal to 0 does not guarantee, it is a maximum or minimum. So if I look at, say, y is equal to x cubed, what we know is that, the graph of this thing looks like this. Kind of flattens out there, and then it kind of goes back up. Notice that the slope here at this point, at x equals 0 is going to be equal to 0. We could kind of verify that. If I wanted to find, y prime would be equal to 3x squared, and we can see if I set this, set this thing equal to 0, this is going to give me x is equal to 0. So we know that its derivative is 0 at this particular point here, but this is not a local extrema because, around its neighborhood, if I'm saying like just even around that point, some points are above and also some points are below. And for it to be a maximum or a minimum, it says that all the points, in that particular domain region or that particular neighborhood have to be either above if it's a local minimum or below if it's a local maximum. So that's why we call them critical points as opposed to maximum and minimum points, because they're simply candidates for our possible maxes and mins. I did also want to explain why I talked about this undefined part as well. Functions aren't always smooth. You can look at an absolute value function, something like y is equal to the absolute value of x, and we know that this function has that V shape. And we can see that, the derivative would be undefined there because it's, the derivative wouldn't be continuous. It'd be -1 here and then it'd be +1 here. If you graphed its derivative function, it would look like this, and it's not a continuous function at 0. So that's why, its derivative is undefined at this point, but you can see that this is a local minimum. So that's why I throw the undefined there as well. So finally, the main objective of this is how do we determine an absolute maximum and minimum, or how do we determine extreme values of a continuous function on a closed interval? So this is the set of steps that we're going to use to be able to determine these. So First, we're going to find all the critical values. So, we're going to figure out where, f prime of x is equal to 0 or, undefined. We're going to identify the endpoints of the closed interval. Now, many examples, they're going to give you the endpoints. They give you the continuous function. They're also just going to identify the endpoint. So sometimes they're identified for you. Other times they might give you a function that actually is closed by by the nature of its own domain. And I'll have my last example will be about that. I'm not going to give you endpoints. You actually have to find them. And last, once we know, its critical values, we know its endpoints, we're going to plug these things back into that original function, and, the largest one is going to be the maximum, and the smallest one is going to be the minimum. Now, it's okay. We might have more than one maximum, as long as it gives you the same, biggest number. So that's how we're going to do this. I'll go through, 5 examples and do it. All right, so we'll start real simple. So determine the absolute maximum and minimum of f of x is equal to x squared plus 1. So I guess we'll call this A because we have steps 1, 2, and 3. So step 1, what I want to do is I want to find critical values. So I know that happens when f prime of x is equal to 0 or it's undefined. So the derivative of this, f prime, is going to be 2x. I'm going to set that equal to 0, so I'm going to get x is equal to 0. And it's not undefined anywhere because, its derivative happens to be a continuous function. 2. I need to find the endpoint. So I didn't describe them. So on the interval from, like I said, most of your examples are going to give you the function. They're also going to give you the interval. So let's say from like minus 3 to 2. So in them giving you this closed interval, they have identified exactly what these endpoints are. So I have an endpoint of minus 3, and I also have an endpoint of a positive 2. So these are my 3 candidates for your extreme values. So what we're going to do in our third step is we're going to plug these things back into the original function. I'm going to figure out what one is the biggest and what one is the smallest. So let's plug in, f of 0. Let's figure out what f of negative 3 is. And also figure out what f of positive 2 is. So remember, it's going back into the original function because this is where I want to find the biggest and smallest number. Or output, to be more specific. So 0, this is going to be 0 squared plus 1. So this is equal to 1. For negative 3, this is going to be minus 3 squared plus 1. So 9 plus 1 would be equal to 10. And then 2 is going to be 2 squared plus 1. So 4 plus 1 will be equal to 5. So remember, the largest number is going to be your absolute maximum. So I can see that this is my largest output. So this is your absolute max. And this is the smallest output that we get, so this is going to be your absolute min. Now they might want more than that. In the next couple examples, I'm just going to label this as the absolute max and this is the absolute min. But, some people might want to say, say the absolute max is 10 at x equals negative 3. So really when we're talking about a maximum and minimum, we're mostly identifying its output value. So, this being the maximum this thing reaches. And it happens at x is equal to negative 3, but, the max is 10. And we might say the absolute minimum is, it's 1 at, x is equal to 0. So, this is its maximum value, this is its minimum value. So, from now on, I'm just going to write these, and we know that the outputs are their max and min values. So, let me do the next example. All right, I decided to stay on the same polynomial path because they're really nice to work with for the first couple examples. So, the first thing we want to do is find critical values. And polynomials are easy to take derivatives of. So, this happens when, f prime of x is equal to 0 or undefined, but derivative of polynomial will be a polynomial, so it won't be undefined. So its derivative is 4x cubed minus 36x, and I'm going to set that thing equal to 0. Now I'm going to try to factor this so I can see that they share a 4 and also an x. So 4 and x, then I'll be left with x squared minus 9 is equal to 0. And this is a difference of squares, so 4x times x plus 3 times x minus 3 is equal to 0. So I get critical values of x equals 0 because of this one. Really, it's only the x factor. The 4 is a constant. X is equal to negative 3 from that binomial, and x is equal to positive 3 from the other. So these are 3 candidates. Our other candidates, I keep forgetting to do this, so this is going to be on, I'll do it at symmetric intervals. So let's say from -5 to 5. Again, the book will give you this most of the time. So basically, when they give you the interval, or the closed interval, they've given you the endpoint. So my 2 endpoints being x is equal to -5 and x is equal to +5. And what I have to do now is I have to plug in, well, these 5 candidates into the original function and figure out what one is the biggest and what one's the smallest. So I'll just go in order. So what is f of 0? Well, this is going to be 0 to 4th minus 18 times 0 squared. Well, I got that one in my head. That's 0. F of -3 is going to be minus 3 to the 4th minus 18 times minus 3 squared. I'll determine that in a minute. F of +3. What's nice is since its derivative is since the function's a even function, this will be the same value. So I'll have to do it twice. Squared. I also have to do -5 and 5. So again, since it's an even function, once I know this value, I'll also know this value. We'll figure out one's our biggest and smallest. Let me determine these. All right, here's a trick that you might want to use with in a regular calc class. What we do is we're trying to use calculus to do this. So what I do is I plug this into the y equals spot. And then what I can do is I can evaluate these points really quickly by just using your table. So instead of graphing, if you hit second table, but before you do that, you have to make sure that the second button that says window, second window, make sure that that first independent says ask. So just tab down, make sure it says ask. So, second table, I'm just going to plug in these numbers. So I know what 0 is, so -3, 3, and you'll see I get the same thing. It's an even function, so -5 and 5, same numbers. So I get -81 for both of these, and I get 175 for both of these. So what I'm looking for is I'm looking for the biggest and smallest numbers, and I can see these. Actually, this is the largest number. This happens to be the same largest number, so both of these happen to be the absolute max. And looking at the smallest number, it's not 0, it's actually -81, so both of these happen to be your absolute minimums. All right, so let's do we'll do a trig function, exponential, and then we'll have a radical, and then we'll finish off with those last 3. All right, so I want to find again the extreme values of sine of x on this closed interval for pi/6 to 4pi/3. So really the same steps again. Step 1, find the critical values. So this happens when f prime of x is equal to 0 or undefined. It's a trig function, so it's smooth. So this is going to be the cosine of x is equal to 0. And I know that the cosine of x is going to be equal to 0. And if you remember your unit circle, the cosine value being, your x coordinates. So we can see that it's going to be here, and here is when the cosine is going to be equal to 0, because we're going to have 0 for that coordinate and 0 for this coordinate. And then, all rotations of 360 or 2 pi from that. So I know this happens to be pi/2. This happens to be 3 pi/2. But remember that we have to have the angle that happens to live inside this, predefined closed interval. And I can see that, 4 pi/3 is actually right there. So this 3 pi/2 is not part of it. So the only angles we're going to go is we're going from, pi/6 is right here to 4 pi/3 right here. We only need to be along that edge. So this is the only critical value on that particular closed interval. So for this case, the only one is going to be x is equal to pi over 2. Now 2 is just giving you the endpoints. We have pi over 6, and we have 4 pi over 3. So last, number 3, we just have to evaluate the original function. Be careful, don't plug it into the derivative. That happens sometimes with my students. We're trying to find the maximum minimum of, the original function, which happens to be the sine of x. So these have to go back into here. So what is the sine of pi over 2? What is the sine of pi over 6? And what is the sine of 4 pi over 3? So I know that the sine of pi over 2 is going to be 1. You actually can see it here, right? Because it's 1. The sine of pi over 6 is going to be a half. And the sine of 4 pi over 3 is minus root 3 over 2. So again, remember your absolute maximum and your absolute minimum. Your maximum being the largest value. The largest value being this thing right here. So this is your absolute max. And your absolute min being this thing right here. Now, many books will ask you to, to graph this in your graphing calculator just to make sure that this makes sense to you. And what we know is, if I'm looking at the sine function, our sine function looks like, here, 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 back here. So when we do our sine function, we know that practice this in a pre-calc class. This is angle 0, this is pi over 2, this is pi, 3 pi over 2, and finally 2 pi. Now, it didn't ask us to take, that full cycle. What it's asking us to do is to go from pi over 6, which would be right here. So that means I don't need all of that. I need just pi over 6. And it wants us to stop at 4 pi over 3, which is going to be about right here. So I don't need all this. We have to stop it at 4 pi over 3, which is going to be this. So we don't need 3 pi over 2 or 2 pi over 3. We need this 4 pi over 3. And what we can see is, in this case, it was the critical value that gave us the absolute max, and it was actually the right endpoint that gave us the absolute minimum. And it's really verified through that picture. That's why we get these particular values. This having a height of 1, this having a height of minus root 3 over 2. That's why the maximum is 1 and the minimum is negative root 3 over 2. 2 more examples. All right, so exponential. F of x is equal to 3dx on this closed interval from 1 to 2. So again, continuous function on a closed interval. It will have an absolute max and absolute minimum by the extreme value theorem. Now, first we have to find its derivative. So knowing the derivative of this function, remember that the derivative of 3 to the x will be 3 to the x multiplied by the natural log of 3. So it's very similar like e to the x. Derivative of e to the x is e to the x, but if it has a different base, it has to be followed by the natural log of that base. And this is equal to 0. Actually, kind of verification of why the derivative of e to the x still works. It'd be e to the x, natural log of e, and the natural log of e will cancel, so it'll just be e to the x. All right, I have to solve this for 0, so I'm going to divide by that constant. So 3 to the x is equal to 0. And what we know is that if you remember the graph of an exponential function, which will actually kind of verify this maximum minimum, if I was going to graph 3 to the x, it's going to look like this. And we're really asking, when is it going to be equal to 0? When is it going to cross, this? But we know that exponential functions have horizontal asymptotes at 0, so this has no solution. Which means this function is defined everywhere, so it's never undefined, which really means that this function has no critical points. So, no critical points. So all I have to do is test the endpoints. I have x is equal to 1, I have x is equal to 2. What's interesting is if it has no critical points, really what this means is this function is going to be it's going to be monotonic in this case because it's always either going to be increasing or always going to be decreasing. I just happen to graph 3 to the x here so you can kind of see when we show this on that closed interval, it's always increasing, monotonic increasing. So when I test this, I have to test f of 1. I also have to test f of 2. Well, f of 1 is 3 to the 1. F of 2 is 3 squared, so the first one is going to be 3, and the next one is going to be 9. A lot of times in my calc classes, I like to do like a negative 1 here instead of a positive 1. So if that was a negative 1 instead, just to make sure people understand that 3 to the negative 1 is actually a third, like I really harp on, what it means to be a negative exponent. So if this was negative 1, then that would still be our left end point, and then this would give us a 1/3 as opposed to a 3. And we can see that this is your absolute minimum, and this is your absolute max. And we can also tell if I was talking about this from, negative 1 to 2, we'd see that it'd be closed here, it would be closed here, and that is my minimum, which would be a third, and that would be maximum, which would be 9. All right, last example, and this is probably one of the more complicated ones because it's got radicals, so this is probably the most interesting. All right, we'll close with this. I did notice that I wasn't changing the letters, so bear with me. There should have been A, B, and C, and D, so please forgive me. I didn't give us an interval on purpose this time because what I'm going to do is I'm going to find that interval in a second here by looking at the domain of this function, and this function will happen to be a function on a closed interval due to its domain. So number one, first thing we're going to find is critical values. And what we can see is that, this is when f prime of x is equal to 0. Let's slide this over. This is going to take some work. So this is when f prime of x is equal to 0 or undefined. We're going to have to use the product rule here. So we know that it's going to be derivative of the first, which is going to be 1, times the second, which is going to be 16 minus x squared, plus the first, which is going to be x, times the derivative of the second. Notice that this is 16 minus x squared to the 1/2. So when I take the derivative of the second, this is going to be 1/2 times 16 minus x squared to the negative 1/2. That takes care of this part. Then we still have to multiply by the derivative of what's inside here, which is going to give us a negative 2x. So this is going to be a fraction because I have a negative power here. So let's rewrite this. Square root of 16 minus x squared plus, at least those 2's will cancel through multiplication. But this is going to actually not be a plus, it's going to be a minus because I have x times a negative x. So this would be minus x squared. And since this has a negative power, it means it's in the bottom, and a 1/2 power means square root. So I have a radical on the bottom of 16 minus x squared. Which actually means this thing was going to be undefined as well. So, I get to write or undefined. Now, in order to figure out whether this is equal to 0 undefined, I'm just going to keep saying 0 right now. But I want to combine these two fractions. So it means I'm going to have to do top and bottom and create a common denominator. So what I'm going to do just to this piece right here is I'm going to multiply this by the square root of 16 minus x squared over the square root of 16 minus x squared, because I want the same denominator as this. Got a little bleed here. Didn't help. Well, so top and bottom by this right here. So what that's going to give me is when you do square root of 16 minus x squared times the square root of 16 minus x squared, you're going to get 16 minus x squared. It's going to have that bottom here, which is the square root of 16 minus x squared. Minus, I'm also going to have this x squared all over the square root of 16 minus x squared is equal to 0. This problem is on every one of my exams, by the way. I'll change some numbers, but I love this example. So now they have common denominators, so 16 minus, well, it's going to be negative x squared, negative x squared. I'm going to get 2 of those, so this is going to be 16 minus 2x squared all over the square root of 16 minus x squared. Now, when I'm setting this equal to 0, I know that this is what happens when the numerator is 0. That's how I get a 0 fraction. So this is when 16 minus 2x squared is equal to 0. You can factor, or since it's since there's only one variable x squared, you can, the square's been completed essentially. You can go 16 is equal to 2x squared. Boy, it'd be so much better to factor, but too late now. So 8 is equal to x squared. So x is going to be plus or minus the square root of 8. And for those who love to rationalize, plus or minus 2 root 2. Now, this thing is undefined, so when I say or undefined, that would happen when the denominator is equal to 0. So the only way the denominator would be equal to 0 is if the radicand was equal to 0. So that means 16 would be equal to x squared, so x would be equal to plus or minus 4. Number 2. We have to find this closed interval, and we're going to do that through the domain of this function. So if you look at the original function, since it has a square root in here, I know that the domain happens only when the radicand is greater than or equal to 0. So the domain is going to be when the radicand is greater or equal to 0. The radicand being 16 minus x squared is greater or equal to 0. Now, if you don't remember how to do inequalities for your quadratics, what we know is that this is up 16 and it's going to drop down like that. That 16 minus x squared looks like this, and I want to know when this thing is greater than or equal to 0. Notice that that is not the graph of this. This is just the graph of the radicand because I'm trying to solve this inequality. So I need to know what these values are right here and here. Well, we just happen to find their zeros. Those are going to be plus or minus 4 because that's when it's going to be equal to 0. So this is going to be negative 4. This is going to be positive 4. So I can see that this is greater than or equal to 0. Well, only for this part of it, from here to here, including these endpoints. So this is going to happen from, minus 4 to positive 4. That's going to be the interval for which this is greater than or equal to 0, which means it's going to be the domain of this thing. Or function f. So these are my endpoints. So finally, number 3, what I'm going to do now is I'm going to plug in the candidates into the original function. I happen to get those candidates twice to the endpoints, but these in here. So I need to do what is f of, I have plus or minus 2 root 2 would be better. I'm going to use negative root 8 because I think it'll be easier to evaluate that. I also have positive root 8. That looks like an odd function. I bet you those would be opposites. We'll know in a minute, won't we? We also have f of negative 4 and also f of positive 4. Because we have to do, these endpoints as well. All right, so evaluating the original function at these candidates yield at negative square root of 8, it's going to be, x, which is negative root 8. X is going to go in here as well. So looking at this is going to be squared is going to make it positive. So root 8 squared is going to be 8. 16 minus 8 is going to be the square root of 8 times the negative of the square root of 8. So root 8 times root 8 is going to be 8, but I still have this negative sign. So that's why this is negative 8. This is an odd function. So if this is negative 8, this is going to be positive 8. And similarly, plugging in negative 4, well, this is going to be 16 minus 16, which should be 0. So this will be negative 4 times square root of 0 is 0, which will give us 0. This will give this the opposite of 0, which is still 0 because it's that odd function. What we can see is that we have an absolute minimum, which would be the smallest number right here. This is our absolute min, because it's negative 8. And this is going to be our absolute max, because it's our largest value. And that's it. Have a good one.